April 1843. Southern Hemisphere. Astronomers noticed something impossible. A star they'd been watching for years suddenly blazes brighter than almost anything in the night sky. Only Sirius outshines it. For weeks, it stays there. Magnitude -1, the second brightest star visible from Earth. Then it starts fading. By 1868, it had disappeared completely. Drops below naked-eye visibility. Everyone assumes it's dead. A supernova, a dying star's last gasp before oblivion. Except, it's not dead. 170 years later, it's still there. Still burning. Still refusing to die. This is Eta Carinae, the star that survived its own death. Now let's break down this mystery and see what actually happened. The early warnings. When astronomers first catalogued Eta Carinae in the 1600s, it glowed at a steady fourth magnitude visible. Unremarkable. Then it started acting strangely. It brightens to second magnitude. Then fades. Brightens again. Fades again. It begins a steady climb. By 1827, it reached first magnitude. Stars don't behave like this. They don't just brighten and fade. Something was wrong. December 1837. British astronomer John Herschel observes from South Africa. He's shocked to see Eta Carinae outshining Rigel, one of the brightest stars in Orion. Then it fades. For 5 years, the star dims. March 1843. Eta Carinae explodes into brilliance again. For 3 days, it becomes the second brightest star in the entire night sky. Peak brightness, magnitude -1.0 from 7,500 light-years away. This star is outshining nearly everything in the galaxy. The Great Eruption has begun. The Great Eruption. For the next 20 years, Eta Carinae stays brilliant. During that time, it ejects between 10 and 40 times the mass of our Sun into space. Material blasts away at 650 kilometers per second. Over 1.4 million miles per hour, the energy released? Nearly as much as a supernova explosion. Supernova explosions destroy stars, rip them apart completely. Eta Carinae released supernova-level energy and somehow stayed intact. Astronomers call this a supernova imposter. A star that looks like it's exploding, releases enough energy to actually explode, then survives anyway. The ejected material forms 2 massive lobes moving outward in opposite directions, creating a dumbbell shape. Astronomers name it the Homunculus Nebula. Each lobe contains several solar masses of gas and dust, expanding at over 1.5 million miles per hour. By 1858, the star starts fading. It drops below naked-eye visibility. For most observers, it vanishes. A smaller eruption briefly brightens the star. Then it fades again. By 1900, Eta Carinae settled at magnitude 7.6, too dim for the naked eye. Hidden behind the dust, it expelled. Astronomers assume it will stay dim forever. Maybe slowly fade away. They're wrong. The comeback Eta Carinae is brightening again. Not dramatically, just a slow, steady increase. The brightening continues decade after decade. By 1999, it reached magnitude 4.8. The brightest it's been since the Great Eruption ended. The dust around the star is thinning. Light that was blocked for over a century is finally escaping. Then, astronomers discover something else. Scientists detect a 5.54-year cycle in the star's brightness and X-ray emissions. Too precise to be random, it's a binary system. 2 massive stars orbiting each other. The primary star, at least 90 times the mass of our Sun, already lost 30 solar masses through eruptions and stellar wind. The companion, 30 to 80 solar masses. hot, luminous. The orbit is highly eccentric. At closest approach, they're separated by only 1.6 astronomical units, about the distance from the Sun to Mars. At their farthest, they're 30 astronomical units apart. This binary interaction explains everything. Why it didn't die. Most stars don't survive eruptions like the Great Eruption. They explode as supernovae. Eta Carinae survived because it's a binary. When the companion star gets close during periastron, its interaction triggers instabilities. The primary star's outer layers pulse. Material gets ejected. The star survived by shedding mass instead of collapsing completely. Like releasing pressure from an overinflated balloon. Right now, Eta Carinae is still losing mass. The primary star sheds one solar mass every 1,000 years through stellar wind alone. That's 100,000 times more than our Sun. The winds from both stars collide between them, creating a shock zone that emits X-rays and gamma rays. During periastron, the X-ray emission drops. As one star blocks the collision zone, astronomers have watched this happen multiple times. 1998, 2003, 2009, 2014, 2020. Every 5.54 years, like clockwork. The system is stable now, or as stable as a hypergiant binary can be. What comes next? Eta Carinae is living on borrowed time. The primary star is a luminous blue variable, one of the rarest, most massive star types in the galaxy. Only a few dozen exist in the entire Milky Way. These stars are fundamentally unstable, walking a tightrope between staying together and exploding. Eventually, the star's core will reach iron. When that happens, fusion stops. The core will collapse in less than a second. Supernova, maybe even a hypernova. From 7,500 light-years away, it would peak at magnitude -4 or brighter, as bright as Venus, visible during the day. The explosion might also produce a gamma-ray burst. Twin beams of radiation are shooting from the star's poles at nearly light speed. If one points at Earth, the gamma rays could damage our atmosphere. Fortunately, Eta Carinae's rotation axis doesn't point directly at us. We're probably safe. When will this happen? Nobody knows. It could be tomorrow. It could be 1,000,000 years from now. Here's what makes this star so important. It's a preview. Every star more massive than about 40 solar masses will eventually become a luminous blue variable, shed huge amounts of mass, possibly trigger supernova imposter events before the real explosion. Eta Carinae is the closest example we have. We're watching the final stages of a massive star's life in real time. The star tried to die in 1843 and failed. Next time, it won't survive. The Great Eruption scattered 10 to 40 solar masses into space. The supernova will scatter the rest: carbon, oxygen, iron, gold. Every element is heavier than helium. That material will drift through space for millions of years, eventually mixing with gas clouds, collapsing into new stars, new planets, maybe even a new life. Eta Carinae refuses to die quietly. When it finally goes, it will seed the galaxy with the building blocks of future worlds. The star that survived its own death will create countless new beginnings. Want to explore more cosmic extremes? Subscribe and hit the bell. We're covering rogue planets next, then the universe's largest black hole. Drop a comment on what we should tackle next. The most violent stars don't die easily. They go out fighting.